Let us now start with the most feared concept in control systems. What is that? The Nyquist criteria, right? Nyquist stability criteria. So we have already seen the polar plots. The polar plots were plotted from 0 to infinity, right? This is polar plots. Now in order to find out the stability analysis using these polar plots, 0 to infinity is not enough. We need minus infinity to plus infinity. And for this reason, we sometimes call them as Nyquist plot, but both of them necessarily they are nothing different, which is why the naming sometimes they are used interchangeably. Okay. But the only thing that you need to remember is for stability criteria, you will need minus infinity to plus infinity. For stability analysis, you will need minus infinity to plus infinity. 0 to infinity is not enough. So the stability criteria we have already seen in RH criteria, and also root locus technique also. Using root locus technique also, we were able to analyze some stability aspects. If the root locus crosses over to the right half of the S-plane, then it will become unstable, and so we will avoid, let us say this is the root locus, okay, and only we will take only those location of roots which will give this part of root locus. Beyond that we are not going to allow, right? So using the root locus also we can analyze the stability, but those are all time domain stability analysis. The RH criteria and root locus, they belong to the time domain analysis, whereas in frequency domain we will be dealing with the frequency, that is omega. That is the Nyquist stability criteria as well as the Bode plots, and there are some others as well. These are what we are going to discuss. We will start with defining a few terms, okay. So first one is the CLTF. This is the closed loop transfer function. So that means there is a forward path transfer function G as well as a feedback path transfer function H, okay. Here we have input and here we take out the output. Then what will be the transfer function here for a negative feedback system, which is what we usually consider? This transfer function is G by 1 plus GH. So this is called as the closed loop transfer function. Then what about open loop transfer function? So just because it is written as open loop doesn't mean that it is the transfer function of a non-feedback system. It is the term that is relating associated with closed loop system only. So what is that? G into H. The forward path transfer function into the feedback path transfer function will give you the open loop transfer function, okay. So this is GH. Then next, what is the characteristic equation? Some of these terms you already know, we are just revising here. The characteristic equation is the denominator of the closed loop transfer function, right, equated to 0. That means 1 plus GH is equal to 0 is the characteristic equation. Now this open loop transfer function, let us represent it in terms of the numerator function and the denominator function, right? There will be some numerator, there will be some denominator. So we are taking it as a numerator, we are taking it as a function of S. So we are writing as n of S, and the denominator function we are taking as d of S. Then what will happen to 1 plus GH? This can be written as 1 plus n of S by d of S. So here the numerator function will be d of S plus n of S divided by d of S. So what you can see here is that the denominator of GH, that is the open loop transfer function, and the denominator of the characteristic equation, not the closed loop transfer function, characteristic equation, both are same. So from here we will have some more conclusions. So what are those? The poles of g of s h of s is same as poles of 1 plus g of s h of s. Okay. Then what about the zeros? Are the zeros same? Zeros means you have to equate the numerator function to 0, right? So here the numerator function is n of s, here the numerator function is d plus n. So the zeros are not the same. Zeros of g of s h of s are not the same as zeros of 1 plus g of s h of s. So these are all some points that we need to be clear about before we start discussing about the stability criteria. Okay. Then we know that 1 plus gh is the denominator of closed loop function, right? This is denominator of closed loop transfer function. You can write CLTF. This is simply the open loop transfer function. Okay. So if you equate the zeros of 1 plus gh, that means the zeros of this equation, this numerator, if you equate to 0, whatever roots you are getting, those are the poles of the closed loop transfer function, right? So that is one important observation. The zeros of 1 plus g of s h of s are the same as poles of closed loop transfer function. Next, the next thing that you need to know is the difference between open loop stability and closed loop stability. Open loop stability deals with the open loop transfer function. Any transfer function, if you take any transfer function, the poles should be in the left half of the S-plane. That is the condition for stability. So when you say open loop stability, it means that the open loop transfer function poles should lie in the left half of S-plane, should lie in LHP. This is the short form for left half of S-plane. Okay. Now you can see here that we have discussed poles of the open loop transfer function g of s h of s are same as poles of 1 plus g of s h of s. So that means the stability, the open loop stability can be found from, therefore open loop stability can be found from the poles of open loop transfer function, that is g of s h of s, or the characteristic equation, that is 1 plus g of s h of s, since the poles of both of them are one and the same. Next is closed loop stability. So like the name goes, we are talking about the closed loop transfer function here. Okay. So the closed loop transfer function poles should lie in the left half of S-plane. That is when the closed loop is said to be stable. Okay. So once again, the poles of closed loop transfer function, we can see they are same as the zeros of 1 plus g of s h of s. Okay. So therefore closed loop stability, this is closed loop stability, can be found from zeros of 1 plus g of s h of s. So you can see that with the poles of open loop, with the poles of 1 plus g of s h of s, we can find open loop stability, and from the zeros of 1 plus gh, we have the closed loop stability. Now that we have discussed some important concepts and terms, we will start with the base concept of the Nyquist stability criteria, which is the principle of argument. So what is this principle, and using this how we can get the Nyquist stability criteria? Consider the S-plane, right? In the S-plane, what will be the coordinate axis? What will they represent? This represents the real part of S, and this represents the imaginary part of S. And we know that S is represented as sigma plus j omega. Okay. So the real part of S is nothing but sigma, and the imaginary part of S is the j omega axis. Okay. So if sigma is value is 3, then somewhere it will be here, and omega value, let us say it is 1, then 1 and 3, here the point will be S. So that is the meaning of S plane, right? Next, what you will take is, you will consider the transfer function plane. So that means any function f of s you take. Okay. So let us say f of s, just for the sake of example, f of s is equal to some s square plus 2 zeta omega n s plus omega n square. Let us say this is the function, some function of s. Now if you take the some value of s, let us say 0, 0. If you substitute here, then what will you get? You will get omega n square. So that means for a point which is at the origin of S plane, what is the corresponding point in the f of S plane? It will be somewhere omega n square. So why I am pointing it out on this axis, the x axis? So that is because this represents the real part of S and this represents the imaginary part of S, and omega n square is the real value. That means the f of s function, when you substitute s is equal to 0, 0, you will get a purely real number whose value is equal to omega n square. Okay. So that is how you can map one point to another point. Let us say some other point here, it will give you, let us say this is point A and the corresponding point is you're going to get here. Now for this point B, the corresponding point here, let us say it is somewhere here. Okay. So in this case, it will have a real as well as an imaginary part. So in this way, any value of s that you take, it can be mapped onto the f of s plane. So this is called as mapping of s plane to f of s plane. This is the first thing that you should know, what is mapping. Now we will consider the function f of s. It will have some zeros and poles. So let us say it has 1 0 and it has 2 poles. This is just for the sake of example. Okay, just for the sake of understanding. Now what are the zeros here? Minus z1 is the 0, minus p1 and minus p2 will be the poles. And since it is only 1 0, it will be a real value. And since there are 2 poles, they are the conjugate poles. So why is that? Because conjugate poles or zeros, they will exist only in pairs. Okay. So here we can write the zeros of f of s are minus z1 and the poles of f of s are minus p1 and minus. Now if you take the S plane and you represent the poles and zeros, this is the S plane, and here you have sigma axis, this is j omega axis. The 0 of f of s will be purely real, so you can mark it somewhere here. So we are taking the values arbitrarily, okay, and the poles let us take to be here. Now their real part will be the same, imaginary part also. One will be, if it is plus omega 1, this is going to be minus omega 1. Okay. So this is minus z1, this is minus p1 and this is minus p2. Now what you will do is, you will take an arbitrary plane that is encircling only one of the poles. It is not encircling this 0 or this pole. Only one pole it is encircling. Okay. So let us take the direction to be in the counterclockwise sense. So this path we will write as gamma s. Now all along this arbitrary path, there are different values of s. Now what we want to do is, these different values of s, we want to map onto the f of s plane. Okay. So that means, if this is the f of s plane, then this axis will be the real part of f and this part is going to be the imaginary part of f, and this arbitrary path whatever we have, we want to map onto this plane. So that means, let us say there is a point S1 here. Okay. Then if you substitute s is equal to s1 in this f of s function, in this function f of s is equal to s plus z1 by s plus p1 into s plus p2, then what will be the corresponding value that you will get in the f of s plane? Okay. So the mapping will be, for example, let s is equal to s1, then f of s1 is simply substituting s is equal to s1 in the function. Okay, so this is going to be s1 plus p1, s1 plus p2. So this you will get some real value plus some imaginary value. Now depending on these values, we will be able to get a point here. So this will be f of s1. In this manner, you can plot all of the points that are on this arbitrary path, and similarly you're going to get a arbitrary path here as well. Okay, so this, let us say this is the arbitrary path that you are getting. Okay, and this you will call as gamma f, let us say. Why we getting a closed loop here? Because here also we have taken a closed arbitrary path. Now the next question is, what is the effect of this pole inside the arbitrary path? This 0 and this pole are outside the path. What will be the effect of the zeros or poles which are located outside the arbitrary path, and what is the effect of the pole that is lying inside the arbitrary path on this loop? Okay, the arbitrary path of the f of s plane. So we will understand that now. If you take this point here, f of s1, what will be this angle? The angle that this line is making. What is this line? It is joining the origin and any point f of s1 we are taking for now. Okay, so what will be this angle? This is nothing but the angle of f of s1, right? When you are taking a point in the f of s plane, it will be having a magnitude which is equal to the length of this, right? Length of the line joining from the origin to that point. And what will be the phase? The phase will be the angle made by this line with the x-axis. So this is angle f of s1, we will call it theta. This is theta. But we know that f of s, the function f of s, this is given by s plus z1 divided by s plus p1 into s plus p2, right? So from here we can get the angle of f of s, the phase of f of s from the transfer function. So what will this be? Angle of s plus z1 minus angle of s plus p1 minus angle of s plus p2. If you want the phase at f of s is equal to s1, then this will be angle s1 plus z1, angle s1 plus p1 and angle s1 plus p2. Now what does this s1 plus z1 indicate? If you take the s plane, you can see that the point s1 is here and the point z1 is here. Okay. Now what will be the line joining both these points? This will be nothing but s1 minus of minus z1. So here you are taking the vector in this direction from z1 to minus z1 to s1. Okay. So this is the vector joining minus z1 to s1. Direction is important here. Okay. So that means s plus z1 that we have here, this is nothing but the angle made by vector s1 plus z1. So that means this angle is angle s1 plus z1. Similarly, the line joining s1 and p1, this will be the line. So let me draw the line here like this. Then what is the angle made by s1 plus p1? The angle made will be this angle. So this is angle s1 plus p1. Similarly, this is the angle made by this line will be angle s1 plus p2. Okay. So if you want the angle of this theta, the angle made by f of s1 point, then you will have to know each of these angles, s1 plus z1, s1 plus p1 and s1 plus p2, and then you have to add them according to this equation, right? So that means you have to first, if this is theta 1, then here you will write theta 1. If this is theta 2, then you will write minus theta 2. This is theta 3, then you are going to write theta 3. Okay. So then the angle will be theta 1 minus theta 2 minus theta 3. So that is how the phases are related. Okay. Now, this is the next part of it. We have taken a stationary point and we have found out what is the relationship between the phase of in the f of s plane and how to get this phase from the s plane values. We have all of these angles here. We have to add them accordingly and we will get this theta. So you can write these theta 1 here as well so that it will become more clear to you. Let this be theta 1, let this be theta 2 and let this be theta 3. Then what will you get? Angle f of s1 will be equal to theta 3 minus theta 1 minus theta 2, right? Now if this much is clear, then you can go to the next part. If it is not clear, then you just rewind and listen to the video again, listen to the lecture again. Okay, because if you don't understand till this point, the next part will become even more difficult to understand. Okay, so let us recap a little bit now, a little brief. We have taken an arbitrary path in the s plane, which is encircling this pole, one of the poles. The other 0 and the other pole are outside the arbitrary path. Now the same path we have mapped onto the f of s plane using which function? F of s is equal to s plus z1 by s plus p1 into s plus p2. Okay. So when you substitute any point s1, let us say, in this function, then you are going to get a corresponding point on this f of s plane, which is going to give you this closed loop. You're getting a closed loop because this is also a closed loop. Let us now consider this s1 point to be moving along this path. Okay, so that means, very simply put, we are taking different points on the arbitrary path in this manner. Okay, and each of that point we are just naming it as s1. Okay, now what happens? As the point moves along the path, what will happen to this vector? This angle is how much? Angle s1 plus z1, right? Now, if s1 is at a different point, let us take it a little distance away from this original point. We are going in this counterclockwise sense, so I am considering a point in that direction only. Okay, so let us say this is the next point. Okay, then what will be the new vector? The s1 plus z1 vector will now be like this. Okay, in this manner, once again you take another point. Then what will happen to the vector? It will move like this. Okay, so in this manner, as the point s1 moves along this arbitrary path, we can draw the vectors for different points like this. Okay, now the question is, as s1 completes an full cycle, that means it started from this point and then it is traveling and then coming back to the same point, then what is the angle that is covered by this vector? The angle covered means from here it is starting, let us say it has gone from here to here, then the angle will be this. By the time s1 comes back to this point, then this vector is just moving around and it is coming back to this point only. So you can say initially positive angle movement was there, but after a point it is coming back and negative angle generations will be there, and finally it will become 0. So that means this is the important point here. As s1 travels along the arbitrary path gamma s and completes a full cycle, then the angle generated by the vector s1 plus z1 will be 0. So that means the net angle generated is 0. The same thing you will notice for this vector s1 plus p2 as well. Okay, so you can draw the vectors like this and then you will see that the total angle generated will be 0. Okay. So similarly, for S1 plus P2 also, the angle generated will be 0. But this P1 point, this pole is going to be different. Why is that? In order to understand that, we will draw it once again. First, we will consider this point, that S1 is at initially this point. Then what will be the vector here? This will be the vector. Now let us say it has moved to a new point. So this will be the new point. So this will be the vector. In that manner, you can keep drawing all of the vectors till it comes back to the same position. Then what is the angle generated? The angle generated is going to be, it is starting from here, it is going in this direction, it is coming back to the same point. Then what is the angle generated? Here the angle generated is a complete 360 degrees. Okay, this is the angle generated by P1 when S1 completes one full cycle. So what is the conclusion here? A pole or a 0, we could have taken a 0 also, right? Here we could have taken a pole and here we could have taken two zeros. So a pole or a 0 which is inside the arbitrary path gamma s will generate a 2 pi or 360 degree angle when S1 completes a full cycle. Now what is the significance of this? The significance lies in the loop that we have mapped on the f of s plane. Okay. So as S1 completes a full cycle, f of S1, the corresponding point, will also complete a full cycle. Then what will happen to the phase of f of S1? So S1 completes full cycle implies that f of S1 also completes completes full cycle along gamma s in the s plane. So then correspondingly f of S1 will complete a full cycle along gamma f in the f of s plane. Okay. Then here the angle generated by f of S1 is equal to the angle generated by S1 plus Z1 minus angle generated by S1 plus P1 minus angle generated by S1 plus P2. And why is that the case? Because angle f of S1 is given by angle S1 plus Z1 minus angle S1 plus P1 minus angle S1 plus P2. So correspondingly the angle generated during the rotation will also follow the same condition. Now the angle generated by S1 plus Z1 was 0, by S1 plus P2 was 0, but by S1 plus P1 was 2 pi radians. So that means in this case here angle generated by f of S1 is equal to minus 2 pi radians or minus 360 degrees. So if the angle generated is minus 360 degrees, then what it means is that the origin will be inside the arbitrary path. Only then we can say that the angle generated is 2 pi radians, right? So using the same trick, right? Let us say the point f of S1 has moved to here. then what will be the new vector now in this direction? Okay, so this vector will now change like this, but what will be the angle generated by this vector? It will be 0 if the origin is outside the vector. So that is why it should be, origin should be inside. So you can draw something like this. Okay, so this is gamma f. The origin is here. Only then, as f of s1, let us take f of s1 to be here, and as f of s1 will move along the path, it will cover 2 pi radians. Another point that you can see here is it is covering minus 2 pi radians. That means it is going in the clockwise direction. Okay, so this will be the direction of gamma f. So the final point you can write here, therefore origin should lie inside the gamma f loop, and also the sense of direction is opposite to that of gamma s. This is because of the negative angle, and negative angle you are getting because it is a pole. If it was a 0, then you would have gotten a positive angle, right? So in this equation you can see that the 0 is positive, the poles have negative values. So if a 0 is inside the gamma s, then a positive angle will be generated. So then gamma f will be enclosing the origin, but the sense of direction will be in the same direction as gamma s. Okay, so this is the basic idea, and now we can write the conclusion. So what is the conclusion? Let f of s be a single valued means for each and every value of s there is going to be a unique value of f of s. Okay, so that's all. Let f of s be a single valued function having finite number of poles and zeros. Then consider an arbitrary closed path gamma s in the s plane which doesn't pass through any poles or zeros. So when we have taken the counter, it was not passing any zeros or poles. That means none of the zero or the pole was lying on the contour. This point is important. Okay, so consider an arbitrary closed path in s plane which doesn't pass through any of the zeros or the poles of f of s. Then the corresponding closed path gamma f mapped onto the f of s plane encircles the origin as many times as the difference between number of zeros and poles of f of s that are encircled by gamma s in s plane. This is the final point, which is also called the principle of argument. This is what we have been discussing till now. Okay, so what does this difference between number of zeros and poles mean? So you can once again just draw the gamma s path. Let us say this is a gamma s in the s plane. Okay, now if there is one pole, let us say. Then what will be the angle generated by origin? Angle generated by origin in f of s plane will be minus 2 pi. What if there is a 0 also inside? Then what is going to happen? Minus 2 pi plus 2 pi will come, because the 0 will generate a positive 2 pi angle, this will generate a minus 2 pi angle, then the resultant you are going to get 0. Now if you add another pole, then the angle will become minus 2 pi. Okay. So in general, how you can write is, if there are p number of poles, so let us say there is another pole here, and like that there are p number of poles. Let there be p number of poles inside gamma s, and let there be z number of zeros inside gamma s. Then what will be the angle generated? Then angle generated by origin in f of s plane is going to be z times into 2 pi minus p times into 2 pi, which you can write as 2 pi into z minus p. Okay. So that means 2 pi will be one encirclement once the origin will be encircled. Z minus p times will be the number of encirclements. Okay. So 1 2 pi means that origin will be enclosed once. So let me draw it to you, it will become more clear. So 1 encirclement means the origin will be encircled once. 2 means it will be encircled 2 times. 3 means 3 times. Okay. So in this manner, z minus p times the origin will be encircled, and that is what is mentioned in the statement here. Encircles, the gamma f will encircle the origin as many times as the difference between the number of zeros and the poles of f of s that are encircled by gamma s in the s plane.